under all these conditions, and then how does it compare to the complementary filter when we saw that under nominal conditions, the two are basically identical. So one is the Kalman filter is a valid alternative for the complementary filter. And then when there is model parameter uncertainty, and since there is degradation also in the sensor, the complementary filter is more sensitive to these changes. And when the two are combined, the Kalman filter is more robust in general because there is less error overall for the, yeah. But we also have to make some consideration that, for example, the complementary filter is much easier to implement than the Kalman filter. And the Kalman filter is also very algorithmically heavy. If the model becomes very, very big, then the complexity of the algorithm increases. And if you have limited resources on your machine, then this could be a problem. Also, the results are the performance of the complementary filter and Kalman filter. I want to remind you that it's similar for the nominal case, especially because they have been tuned under using the same method. And yeah, basically everything is the same. It's just the implementation of the filters is what changes. And so for the future, I would recommend that validate this method further by using, for example, hardware in the loop simulations or piloted flight tests, because the aircraft, the Cessna Citation, it's a real aircraft present here at the faculty, and it can be used, for example, for flight tests using exactly this approach. And also, I've developed in this study a whole architecture for hybrid NDI for the Cessna Citation using both complementary filter and Kalman filter, and this can and is being used already for further studies, and I recommend looking, for example, at adaptive filters this time, which can change the filter parameters, so for example the omega c in real time rather than being fixed for the whole simulation. Also, I recommend including angular acceleration measurements, which were not included in this study. This was the whole issue. So if you have angular acceleration measurements, then you don't have to go through the painful differentiation, which amplifies noise. And also, if you have angular acceleration, you can combine that with IMU to then have accurate estimation of both omega and omega dot. This can be done using angular accelerometers, which are used in high-performance aircraft already. Or if you have a small UAV, you can also use multiple linear accelerometers, and this also can provide a measure of angular acceleration. So this concludes the presentation. I hope it was interesting and you learned something from it, and now we'll open the floor to questions. Thank you.
Thank you, Antonio. So we have time for questions.